Now that we have discussed different ways of realizing integrators, non-invert integrators and differentiators, we will now look at a very important part, a very important aspect, which is how does integrators and differentiators respond to pulse signals. When I feed a periodic pulse signal like this, what will be the response to differentiators and integrators? Now, such functions, where will you encounter such signals? I said in analog function generators. Okay, the signal source generators, which can generate you a wide wave kind of waveforms. It can give you square wave outputs. It can give you triangular waves. It can give you sinusoids. So how do you get all this? We will later see that using a single oscillatory source, we will generate all these different waveforms from using some different op-amp based circuits. And all those circuits, we will later discuss, they are called Schmitt triggers, oscillators, and all those circuits will be discussed at a much later stage. They will all be built using op-amps. So now, to just give you some basics of those mathematical operations that we'll have to make the signal go through to get the square and pulse, square and triangular waveforms. I thought I'll just roughly introduce you to the idea of how integrators and differentiators behave when I feed pulse signals. Okay, so now let's start with this. Let's say I feed a pulse signal and whose average value is 0. Okay, the DC value is 0. Why am I saying this DC value is 0? Because we know that, let's say you have a pulse signal whose DC value is non-zero, which means what your on time and off time will need not be same. Assume it goes from minus V peak to plus V peak. If I have a larger off time than on time, which means it is minus V peak for a longer duration. Let's say 1/4 of the time it is plus V peak. The remaining 3/4 of the time period, it is minus V peak. What is the average value of this signal? Can you guys tell me? What is this average value of this pulse signal? 3/4 of the cycle, it is minus V peak. 1/4 of the cycle, it is plus V peak. No, is it V peak by 2? Check again. Is it right? Yes. The sign is minus, right? So it is minus V peak by 2. Okay. So you can write it. How do you find the average value? Find the integral of this waveform over one full cycle. Okay. Then divide it by the time period. In the positive cycle, it is going to be Vp into T by 4. The negative cycle, it's going to be minus 3 by 4 T into V peak, the whole divided by 1 by T. So you will get minus V peak by 2. Okay, so this will be minus half and you will get minus V peak by 2. So it's a net negative DC. So whenever you have a pulse signal whose DC value is non-zero, and then you are applying this as an input to an integrator, you can always split this signal into a 0 DC average signal and a non-zero and a DC signal. I can write it as sum of two signals, right? I can write it as a sum of a DC signal of value minus V peak by 2. And I can also write it as another signal where I've subtracted minus Vp by 2 from this. So I've subtracted minus Vp by 2 from this. So, okay. So if you add minus Vp by 2, you should get these two waveforms. Now I can treat them as two independent signals. Okay. See, you understand what I'm doing? I just took this signal, which is going from minus Vp to plus Vp. This signal had a non-DC average, a non-zero DC average, which means I can split the signal as two components. The DC point, whose average is minus V peak by 2, and another non-DC or another zero average DC signal whose peak value will be given by V peak plus V peak by 2 and negative peak will be minus V peak plus V peak by 2. So this will be 3 Vp by 2 and the negative half cycle will be minus Vp by 2. Okay. So if you have such a signal, then we can, what will be the average value of this signal? So if I give you the peak value is 3V peak by 2, and the negative peak value is minus V peak by 2, what will be that average value? Assume the same T by 4 for on time, 3T by 4 for off time, 0, right? That you can show it, it's 0. So I'm splitting the signal into two parts, a zero average and a non-zero average. What do you think will happen if I feed this signal minus V peak by 2 to an integrator? What do you think will happen? It will be a linearly increasing signal. Will it be, say, I'm applying a negative DC signal, so output will go positive because it's a not inverting integrator. So output will increase linearly till it reaches the saturation voltage, and after that it will saturate. Okay, it will keep increasing linearly and then it will saturate after some time. Okay, but what if I feed a pulse signal? So let's assume we haven't reached the saturation voltage yet. So if I haven't reached the saturation, then it will keep on increasing as a ramp. Keep that in mind. Now, what happens when I feed a pulse signal to an integrator? When you feed a pulse signal to an integrator, in the positive half cycle, when you feed a pulse signal in the positive half cycle, you will be your output will increase. In the negative half cycle, you are removing, so you can think about it like this. In the positive half cycle, you are supplying some charge to the capacitor. So let V peak be the voltage. Let's forget about let's forget about this signal, 3P by 2 and all that. Let's assume it's a pure symmetric pulse signal. During the positive half cycle, you will have Vp by R, a current will generate in the resistor. This current will be supplied to a capacitor for a duration of T by 2. If I supply this for a duration of T by 2, you are supplying a charge. What is the total charge you are supplying per cycle during this half cycle? How do you find charge? Integral IDT. So the total charge you are supplying to your capacitor is Vp by R into T by 2. Okay. And this is the charge you are supplying to this capacitor in the positive half cycle. In the negative half cycle, what am I doing? See, in the positive half cycle, I'm supplying charge to the capacitor. In the negative half cycle, I'm removing charge to the capacitor from the capacitor. And since the positive area and the negative areas are the same, by the time you come to this point, you started at T equal to 0. At T equal to T by 2, you gave maximum amount of charge to the capacitor. Then you slowly start taking away this charge during the negative half cycle. Okay, slowly you start taking away initially this amount. As time increases, you're going to take away all the charge that you delivered in the positive half cycle. When you remove all that charge, if your capacitor voltage initially started with some voltage, it would have reached a peak value. It would again return back to the same voltage because now you have removed all the charge. Okay, because this current is constant during this cycle, the charge delivered is linearly increasing. So capacitor voltage will also increase linearly. We started with some initial voltage 0. We ended up with the same initial voltage, same final voltage after one cycle. And the same process will repeat forever. So this is what happens when I feed at 0 DC average signal. Okay, at 0 DC average, it will within one cycle, the net charge that you are going to deliver to the capacitor is 0. You start off with some 0 volts, then you will return back to 0 volts. The same will hold true for this waveform also. I can take minus 3 Vp by 2 and quickly show you guys that during the positive half cycle, the slope will be higher. Okay, the waveform will not be symmetric. But if you guys, because we discussed this 3 Vp by 2 and minus Vp by 2, I just want to finish off with that. I don't want to leave that hanging. So if this is 3 Vp by 2 and this is say minus Vp by 2, during the positive half cycle, the total charge that I'm going to deliver is 3 Vp by 2 R times T by 2. In the negative half cycle, okay, sorry, this is times T by 4. T by 1/4 of the duration, I'm delivering 3 Vp by 2. The negative half cycle, I am again removing a charge whose total charge that I'm removing will be minus Vp by 2 into 3t by 4 into 1 by r. See, both the charges are same. So how do you think the waveform will look like? Let's say I'll start from 0 here. Will the waveforms have same slopes? Will the waveforms have same slopes by the end of 0? The waveforms cannot have same slopes, right? Because you're in one cycle, you're injecting a much higher voltage, 3 Vp by R, 3 Vp by 2 is a higher voltage. So you will have a much higher slope for t by 4 seconds and a lower slope for the remaining 3t by 4 seconds, so that at the end of one cycle, you'll start from 0 volts, you'll return back to 0 volts. And this will continue forever. The waveform will look like this. If I wanted, so this is t, this is 2t, and so on. Now, if you add DC signal to this, the response with a DC signal, what change do you expect? See, I've removed the DC. It's just going to be a perfect some asymmetric triangular waveform. The waveform is going to look increase, decrease, increase, decrease. That's what it's going to do. Now, if I add the DC content, Vp minus Vp by 2, what do you expect will happen at the output? Add a ramp signal to this. You will have to add a perfect ramp signal to this. If you add a ramp signal to this, can I say the waveform will look like this? Let's assume this is your ramp. Your waveform should look something like this. So it will look something like this. It will be a waveform that is riding on top of a ramp signal. So your op-amp's output will keep increasing because of the presence of a DC signal. It will keep increasing. It will do this. It will do this. It will increase linearly like this. Okay. Eventually, it will saturate. After it saturates, op-amp will then go out of saturation, out of the linear operation mode, and output will saturate to some constant value. Okay. So that's why when you are feeding such square wave signals, pulse signals to integrators, you remove the DC content. You don't want the output to saturate. So we will remove the DC content. So that's why I'm feeding a signal whose DC average value is 0. Okay, or average value is 0, or I can say DC value is 0. So now we'll come back to analyzing an integrator with an integrator where we are feeding a periodic pulse train as an input to it. Okay, so first, now see, so far we just analyzed intuitively. Let's get the math right. It's given that the signal goes through a peak voltage of V peak and minus V peak. And the time period of this pulse, let's take the whole duration is 1 millisecond. So which means the on time is half a millisecond, off time is half a millisecond. Now you're supposed to plot the output waveform for 3 conditions. RC equals to 1 microsecond, RC is 1 millisecond, RC is 10 milliseconds. So this RC, the integrating time constant, is varying between these 3 values, and we'll see what difference does it make. How will the waveform shapes be different? So start with, assume that initially the capacitor voltages are all 0. So you can assume that your output voltage is going to start at 0. The first cycle you get minus Vp, and then immediately it goes to plus Vp and stays on for half a millisecond. During that duration, what will be the slope with which the signal will raise? Can you say what will be the slope with which the signal will raise? What will be the output voltage? Keep this in mind. Your output voltage is simply minus 1 by RC times integral Vi of t dt. So if you use this result, it will be minus, if I'm applying positive voltage level, the first I'm applying a positive voltage level, so it will be Vp by RC integral 0. We will integrate it for first half cycle, so t by 2 dt. So till this time, it will increase like a linear ramp. So it will be a negative ramp. So positive when VP is positive, so it will be like this. So when VP is positive, your output will be negative. So in this cycle, it will start here, go through a negative value. What will be the peak voltage it will reach? See, at this point, you are delivering full charge, maximum charge is delivered at this point. After that, you are going to remove charge in the next cycle. So the voltage it can reach is maximum at this point. Okay. What will be the value of that voltage? So minus Vp by Rc is the slope at t equal to t by 2. I just need to substitute t equal to capital T by 2. That's when you get that. Now it's given that your t is 1 millisecond. So this is half a millisecond. If this is half a millisecond and RC time constant is given to be 1 microsecond, what do you expect this to go to? Can I say it will be Vp into 500? This RC is 1 microsecond. So 10 power minus 6, which is 1,000th of a millisecond. T by 2 is half a millisecond. So it will be, the final voltage will be minus 500 Vp. So this node voltage goes to minus 500 Vp. Now, when the negative voltage is applied during negative half cycle, the signal will again start decaying. And what will be the voltage at t equal to t by t? At time t equals t, what will be the voltage at this point? 0. It starts at it reaches a minus 500 Vp and returns back to 0. That's all will happen here. So you'll see a waveform which will look like this. Okay. Now, the difference in the peak voltage that you reach is dependent on your time, the RC time constant. If RC equals to 1 millisecond, what will be the peak voltage it will go to? If RC is 1 millisecond, it will go to Vp by RC into T by 2. T by 2 is 0.5 milliseconds. RC is 1 millisecond. What will be the peak it will go to? Minus Vp by 2. So if I have an integrator with a very slow time constant, the time constant of the integrator is same as the period of the signal, which is 1 millisecond. Okay. Then the peak value it goes to is minus Vp by 2. This is fine, right? So all I'm trying to say is, what is the impact of this time constant? This time constant, if you're feeding a pulse signal, then it tells you what is the peak voltage it can reach. Okay. A smaller time constant generally means that you can charge the capacitor very fast. That's all it means. So smaller time constants usually means you will charge very fast. So that's why for 1 microsecond, you're able to charge the capacitor so fast that within that half a millisecond, it reached minus 500 Vp, which is a very large voltage. But for 1 millisecond time period, and the half cycle happens to be half a millisecond, you are able to only charge to half of the input voltage peak, minus Vp by 2. So if I assume 10 millisecond, what will be the peak voltage that it will go to? Nothing will change. The waveform shape, everything will look the same. The only difference this RC time constant will make for a pulse input is the peak value. That's it, 1/10 of this. Because your time constant is 1/10, so it will be minus Vp by 20. Right? It's just the peak value it will go to is minus Vp by RC. Right? That's the it's proportional to minus Vp by RC into T by 2. See, all it matters is that if the thing is that RC will determine your slope. The slope of this signal, right? If you see this waveform, the slope of this waveform is simply Vp by RC. A smaller time constant means larger slope. So the waveform will look something like this. It will reach, if I apply this, let's assume somewhere in the middle, I'm plotting it in the log scales, not properly to scale. This is minus Vp by 2 for a time constant of 1 millisecond. For a time constant of 10 milliseconds, it will be a much smaller peak value. Okay, so it will look like this. So for 500 peak V peak, if it is like this, then it will increase with a much lower slope. If your time constant is 1000 times, I'm showing this on a log scale. Sorry, not on proper scale. So don't take it as this, but all I'm saying is that the peak value will be much lower. It's the same clock signal, but with a much slower integrating time constant. So means it takes much longer to charge the capacitance. So that's what it indicates. For 10 millisecond, even lower. It will go to an even lower voltage within a single cycle. Okay, so this is minus 500 Vp by 2. This is minus Vp by 2. Minus 500 Vp, sorry. Minus 500 Vp, Vp by 2, and minus Vp by 20. Okay, so the integrating time constant tells you the rate at which the input can change. So we'll very quickly analyze. I have a few more problems to solve, but I'll analyze one problem and we'll stop the lecture today. So what happens when I feed a pulse signal to a differentiator? What do you expect at this output? Will it be, how will the impulse train be? So at the positive, whenever your signal is transitioning from minus V peak to plus V peak, you will get a positive impulse train. And at the negative, whenever a signal goes from positive to negative, you will get a negative impulse train, negative impulse signal. It will keep alternating between positive and negative like this. Okay, so that's nothing but differentiate derivative of this signal. Let's say I give you something like this. If your signal, pulse signal, instead of being a sudden step, goes like this. See, all practical pulse signals will have some finite rise and fall times. So if I assume finite pulse, finite rise and fall times, what do you expect the waveforms to look like? Pulse, right? So in this region, it's going to be derivative of a constant, a linear ramp. It's a ramp in this, it will be pulse here. And here it will be 0 because it's constant. The derivative of this constant is 0. So you will get, instead of impulses, you will get pulses. You will get positive pulse and negative pulse. Okay. So I'll just discuss what happens in an ideal, in a practical differentiators is that, or let me just talk about this circuit. So that's clear, right? So if I feed an ideal pulse signal with a finite ramp, you will get a pulse output instead of impulses. Let's say we feed a pulse to a RC signal, RC circuit like this. Assume that the time constant RC is much smaller than the time period of the signal. What do you expect to see at this output? What do you expect? So let's say this goes from 0 to V peak. What do you expect to see here? Use basic logic. A capacitor will act like a short circuit whenever your input undergoes sudden changes. Sudden changes. See, what is this? A step input means the input is changing instantaneously from a smaller value to higher value. If you are to think intuitively, just we know that most signals can be, will it be an impulse train? Think again. So think like this. A step can be represented by an infinite sinusoid, right? A sinusoid of finite frequency, the maximum slope of a sinusoid, slope with which a sinusoid can increase is, let A be its amplitude, omega be its omega naught be its frequency in radians per second, is A omega naught. So if I have to approximate a step function in this region, what should be the frequency of the sinusoid that I should use? Infinity. It's changing instantaneously. So a step input in this region can be treated like a sinusoid at infinite frequency. For any, if you're feeding this to an input to a circuit, that circuit will think a sinusoid of infinite frequency has been fed to me at that instant, at t equal to 0. So you can assume the capacitance is a short circuit. Capacitance acts like a short circuit. So suddenly, if you apply 0 to V peak here, this node will also come to V peak. So your output node voltage suddenly goes from 0 to V peak. The moment this node reaches V peak, resistor is a memoryless element. It's an instantaneous element, meaning the moment you apply voltage across the resistance, it will instantaneously produce a current. And that current will be Vp by R. Okay? That current is given by Vp by R. That current will now start flowing through this capacitor. So what happens when current flows through a capacitor? It starts charging. So initially the capacitor voltage was 0. Now as soon as current starts flowing, the capacitor voltage will start charging. As the capacitor voltage starts charging, it starts at 0. The capacitor voltage will start at 0. And then it will slowly start charging. What will happen to the voltage across the resistor? As the capacitor voltage starts charging up, the voltage across the resistor is simply what? Input voltage minus the capacitor's voltage. So the voltage across the resistor will decrease. So this is what will happen. It will decrease like this. Assume that this RC time constant is much smaller, meaning the charge across the capacitors will charge very fast. That's what time constant smaller means. The charging time for capacitors is very small, which means within the single period, within the time period T, I'm assuming this half period, time period T by 2 is much greater than RC. Which means your RC time constant of the circuit is much smaller. So what will it do? Instantaneously, it will very quickly it will discharge and go to the output voltage will go to 0, and the capacitor will be charged to what will be the capacitor voltage will by the time we reach one half cycle, the capacitor would have been charged to plus Vp volts. Okay. See, all I mean is, see, how long does a RC circuit, if I take a resistor and capacitor in series, how long will a capacitor take? If I apply a sudden step voltage, what is the time taken for this capacitor to charge to V peak? A voltage of V peak volts. How long does it take? Ideally infinity, but practically we take 3 to 5 time constants. Okay, usually within 3 to 5 time constants. In one time constant, it will charge close to 60 to 70. I think close to 60 to 70%. In 3 time constants, you are already at 95%. In 5 time constants, you'll be 99% plus charging. So normally, if I say T much greater than RC, it means that your time period is at least greater than 5 time constants. So in those 5 time constants, your capacitor is now charged to V peak. Now at T equal to T by 2, you have a condition like this. You have a capacitor which is charged to V peak, and your input voltage goes from V peak to 0. It goes from V peak to 0 instantaneously. Output voltage will stay at, what will be the output voltage? So we had a situation like this. Yeah. So I applied 0 to positive. Will see, think like this. Capacitor voltage is V peak. Now your voltage signal has come down to 0 in the first half cycle. Now you are at T by 2. At this time instant, what will happen to the the voltage across the resistor? Will it go through a sudden step? What will be the voltage at that point? Yeah, your capacitor will act like a short circuit. Capacitor voltage cannot change instantaneously. It will act like a short circuit. Okay, it's going to act like a short circuit. So if I suddenly ground this, the voltage across the resistor will become minus V peak. Is that fine? I think one of you got it. See what happens. You have suddenly short circuited the input, but the charge across the capacitor cannot change instantaneously, right? It doesn't have any path to instantaneously go to 0. So previously this node voltage was plus, I mean, this was at plus VP and minus, this was at the, I can say this plate was at a higher potential, and that condition will not change even when your input goes to 0. So when input goes to 0, this will go to minus V peak. So your voltage will be minus V peak across the resistor. Now resistor, now you have a situation like this. You have a resistor, you have a condition like this. You have a capacitor and a resistor in parallel, and the capacitor has a voltage of minus V peak across it. Right? Input voltage is 0, so I can ground it. Now you know that this circuit will be a first order discharge and it will go like this. So the waveform will look like this. So it will go from plus V peak 0, and then it will go to minus V peak to 0, plus V peak to 0, and so on. So this is how the waveform is going to look like for an RC circuit, where the time constant, RC time constant, is much smaller than the signal's time period. Okay? So keep this in mind. The next class, we'll start discussing about differentiators little bit more deeper. Okay?